Okay, I think we are going to start. People are still trickling in, but that's their loss. So welcome to the day 3 of the 16th Recommender Systems Conference. We have paper session 7 for you today, sessions and interaction. And I'm very pleased to introduce Noam Koenigstein from Microsoft R&D. And he'll be talking about Next Basket Repurchasing. Take it away.
Thank you, Robin. Okay, so yes, I'm Noam Koenigstein, and the focus of this talk is going to be recommending repurchased items. And we'll start right away with a problem definition. I assume that most of you are familiar with the problem of the next item recommendation problem. In that problem, we have a context of an existing basket, and the goal is to recommend one more or a few more items that go along with that existing basket. This is different than the focus of this work. We're going to talk about basically recommending the whole basket. So there's no context of an existing basket. There is a user ID and a future timestamp, and the goal is to recommend the entire basket for that particular user. Just one question, is there any way to make the slides that I see slightly bigger because they're kind of tiny here? That's possible? Yes, please, thank you. Thank you very much. Okay, so the next basket recommendation problem has been studied in the past, and we are citing in the paper a very good survey by Ming et al. And they showed, at least in the groceries domain, that the majority of the of people's baskets consist of previously purchased items. And in fact, or as a result, the leading models for next basket recommendations produce recommendations that exclusively consist of previous purchased items. So we decided in this work to actually focus only on items that were purchased in the past, and we dubbed this the next basket repurchase recommendation problem. And I want to talk a little bit about the next basket repurchase recommendation problem. And to start with an example, and I want to consider 2 different users. The first user is a single person, maybe a bachelor living by himself, and the second is a family. Both users purchase toilet paper. The single person buys toilet paper once every 2 months. The family buys it every week. Why is the difference? Well, they have different consumption rate. Now let's look at these exact same users and a different item. The single person likes bananas, and he buys bananas every week. The family buys it every week as well. Why is it different than toilet paper? Because bananas have a shorter durability. Here, the main factor is item durability. The point I'm trying to make is that when you're trying to model repurchases, it's important to learn different buying cycles for every combination of user and item, which is why this problem is complex. And often, metadata like item durability or user demographics are unknown to the recommender system. So at least in this work, we only base our model on previous purchase patterns. Okay, so next I want to investigate some repurchase behavioral patterns. And I'm going to start with the most dominant and maybe basic pattern, which is loyalty. Users are loyal to a particular item or a particular brand, and they repeatedly go back to the store and keep buying that same item that they like, at least in the groceries domain. But this loyalty is not forever, and there is a slow temporal drift in people's preference. And common reasons for that could be just the availability of fresh produce or dietary change, or just a need to cut expenses on behalf of the user. A second common pattern is item correlations. And I assume that many people are familiar with the story about beer and diapers being correlated. And regardless whether they are correlated or not, and when and where, we do notice, and other people as well, that there are strong correlation between different items. And these correlations also imply sometimes a similar buying cycle for these items. However, I do want to note that item correlations could be personal. So for a particular user, several items could be correlated, and not for everybody else. We also saw in the data set, and we discussed this in the paper, there are negative correlations. So items that never go together or hardly ever go together. That is probably the result of the fact that these items are actually alternatives. So two items that represent the same product by different brands. So if you get one, you often don't need the other one. Another point I want to make about repurchases is the importance of modeling explicit timestamps. So when we investigated earlier works, we saw that a lot of them treat that problem and the historical data as a sequence of historical purchases, and they disregard the time that passes between the different historical purchases. And when we look at the problem like that as a sequence and you don't look at the exact timestamps, you can investigate, for example, the correlation between the last basket and previously purchased baskets. And what you see is this decreasing trend, which is the result of the preference drift that I mentioned a few minutes back. However, when you actually look at the exact timestamps, often you get a much more informative picture. So for example, in this user, she probably has a fixed shopping list and she buys it on a weekly basis. And on particular days, the probability to purchase particular items is increased and the correlation increases. And other days, she might go to the grocery store, but may buy other items. So let's go to our proposed method. We proposed a model which is based on a hypernetwork. A hypernetwork is just a network that predicts parameters for another network. So it predicts the weights and configures another network. In our case, in order to learn the user and item buying cycle, we have a hypernetwork F that takes the user representation and the item representation. These are learned as well. It takes these representations and predict a one-dimensional per user per item vector that configures a one-dimensional convolutional layer that scans the user history. So with these per user per item parameters, we have a one-dimensional convolution layer that scans the user history and predicts the probability for buying a particular item by that particular user at a given time step in the future. So essentially, that's the core of the model. It is trained by maximizing the likelihood over historical events and just employing stochastic gradient descent. There is one more component to the model. I'm not going to go in full detail here, but you can read that in the paper. Essentially, in order to enhance the importance of item-to-item correlation and actually the personal item-to-item correlation, we have another component that takes the user history and builds a sort of item-to-item correlation matrix that is added into the model in order to enhance the accuracy and improve the predictions of the hypernetwork. So in terms of evaluations, we considered 3 datasets, Instacart, dunnhumby, and Value Shopper, and multiple baselines, including actually several types of sort of personal popularity baselines that were shown by the objective survey to actually perform very well in this type of problem, actually better than some of the other models that were proposed, and also some state-of-the-art models that were also shown in a general survey to perform better than others, including also 2 ablated versions of our own model. One ablated version was canceling out the hypernetwork in order to show the contribution of the hypernetwork, and the other one canceled out the item-to-item correlation component to show the contribution of that component. Results. We reported Reco, mean reciprocal rank, and NDCG. Basically, I'm not going to go into all of the details. We were able to show that in the vast majority of cases, our proposed model was more accurate than the alternatives. There were a few cases in which a model called TIFU-KNN, that baseline, was actually doing better than our model, and we came second. We were also able to show the relative contribution of using the hypernetwork and its importance in order to learn per user per item buying cycles. And we were also showing the contribution of the personalized item-to-item correlation matrix, that component to the general model. So the last point I want to make here is just to show you how the weights which are predicted by the hypernetwork, how they look like. And this is so obviously the weights are different for every combination of user and item. These are, you can think about it as general weights for a general user and a general item. There are a couple of interesting things to see here. The first one is that in the first 3 days, we actually have negative weights. That implies that in the first 3 days, right after the user bought that particular item, her probability of repurchasing it is decreased. She just got it. The probability of getting it the day after or 2 days after is actually lower than the baseline. And then after 3 days, it's starting to increase and reaches a peak after a week. And you can see that, again, that for that user, that weekly repurchasing pattern. So she has a day for sort of a fixed shopping list or fixed groceries list, which is bought on a particular day. And on those days, the probability of buying that item is actually increased. And the last pattern to see here is this gradual drift or the probability going down, which basically implies that as time goes by, if she hasn't bought that item, the probability of repurchasing it eventually decreases. Maybe she's just not interested, she stopped buying that product or switched to an alternative. So to conclude, we investigated the Next Basket Repurchase Recommendation problem, where we show that it's important to learn buying cycles for every combination of user and previously purchased item. We also show the importance, in this case at least, of modeling the explicit timestamp and not look at the data as just a sequence of historical events. We proposed a model which is based on a hypernetwork that configures a one-dimensional convolutional network. And in this work, we did not use any user metadata or user demographics or item metadata, but we do think these could be useful, and we hope to include them in a future work. So, thank you.
So we do have some questions, and I'm going to ask this one first because it was my question. And that is, you've kind of separated this problem into the sort of a hyper network learning part, and then a regular network. And just was there no way to do those in one model, or what was the advantage of having that separation between those two kinds of learning?
Yes, that's a good question, and we talked about this a little bit in the paper. Because it is, in this problem, what we're trying to do is learn a different buying cycle for every combination of user and item. We discovered that, and there's not tons of data to learn, so hypernetwork is actually an efficient way to kind of have that flexibility without learning too much parameters. You could have good results without a hypernetwork, so that's one of the ablation versions that we have, and it performs pretty well, but you can do somewhat better with this architecture.
Yeah, don't talk to me. You want to talk to the microphone.
Sorry.
Yeah. Okay, let's keep going because I think we got other questions here. One question, could you elaborate more on how user and item embeddings are learned?
Yes, that's actually simple. They're just part of the model, and they're learned as part of the backpropagation process. They are the input to the hyper network, and the learning basically propagates all the way to learn these embeddings.
Okay, and then just one last quick question. Groceries are kind of special in the sense that there's a certain stability to the products and also repurchasing, you know, people have to eat, right? So I'm wondering, and this question is wondering, you know, how might that extend to other kinds of products and situations where you get sort of new products with a little higher frequency?
Okay, so I'll try to answer this. I do have basically the motivation for this particular work. You can think about different uses. What we had in mind is recommending coupons. So by predicting what the user would want to do in a grocery store, we were hoping to kind of recommend coupons in advance. I'm not sure about other domains. The majority of at least the work that I've done and most of the papers that I read in this community deals with recommending new stuff to new users, and maybe I assume that most of the applications and recommender systems are about recommending new items. So I don't know if that extends to everything, but obviously groceries is something that all of us need, and we know that it's, at least in this domain, it is useful. I don't know to say how important it is for other domains, but it would be useful where repurchases occur.
Right. All right, let's thank our speaker again.
Thank you.